check from the initial path. We'll talk about the moduli continuity method from the local pairs.
Thank you very much for inviting me. I thought of this talk kind of summarizes work in 3 papers, and I thought of breaking it in 3 talks and make one now and then one in Shanghai and one in Pohang, but then I thought maybe it's a bit confusing because it's not exactly Game of Thrones that you're going to be thinking about it for months. So I decided to compact it, but since we are starting late, I may have to skip some parts. So I hope that's okay. Right, so what is this of the moduli continuity method? So the problem is to explicitly, whoa, this is terrible, okay, maybe this, much better. So explicitly describe components of the moduli of k-stable varieties or pairs okay by constructing a homeomorphism from this, or more commonly to its analytic counterpart, the Gromov-Hausdorff compactification, to some known space, which usually is constructed using Yeti. So to some known compactification. This usually uses Yeti, usually, or some variant of it. Okay, so this has done for varieties quite a lot at this stage. So for Del Pezzos was done by Odaka Spotty-Sun, and as far as I'm aware, it was the first time this was considered, although probably was a bit based on previous work by Tian. I'm not exactly sure what Tian had done earlier. For Del Pezzo varieties of degree 4, which are intersection of 2 quadrics in Pn for n bigger or equal than, say, 5, I guess, was done by Spotty-Sun. For cubic threefolds was considered by Liu and Su, following work from Spotty-Sun. I may comment something on that later. But for log pairs, it hadn't been considered, and
Two-dimensional degree 4 case is
what's that?
So in 80s, late 80s, Mapuche infected degree 4 two-dimensional.
So that's our Del Pezzos of degree 4, right? Okay. You're right, I actually have read that paper. This is embarrassing. Sure, yeah. Yeah, thanks. Yeah, okay, so for log pairs, I had been thinking of that problem for a while, and basically we had to develop all the technology, and the first problem was that there wasn't a good notion of what you want to do this homeomorphism from was clear, but the natural Yeti compactification wasn't there. So that was the first thing we had to consider. And then by doing that, we realized that we could do it in another more general case, modulus conjecture. So we did that one as well. So today, we'll consider describe this, which I will write for the rest of the talk, GH bar log k stable moduli of compactification of log pairs x1 minus beta d for beta between some beta 0 away from 0 and 1, so in some region close to 1, in two cases. Or at least I will state it in two cases. I may just be able to say much about one because we started late. So first one is when x is del pezzo of degree 3 and d is an anticanonical divisor. And the second one is when x is Pn and d is a hypersurface of degree d for d large enough. Okay. 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 So I'll start by describing. So I'm going to focus mainly on one, and I'll start by describing what's the GIT setting we need to consider. So summary on effective variations of GIT for pairs, for log pairs, or for log Fano pairs. So this is really joint work with Gallardo. So, so we'll consider hypersurfaces of the dimension n in projective space. So all the time, even if I just want to consider this case, a lot of the things apply in general dimension and degree. So it's only at crucial technical points when we are only able to deal with certain situations in which we have to go down to this case for one reason or another, but a lot of it applies in general. So when I can keep generality, I will do that. And this is one of these situations. So consider a hypersurface of degree d in P n plus 1 and a hyperplane. Okay, and we have naturally a parametrization space of these pairs xh given by, well, basically the space of these sections yeah, okay. Okay, so so an element here is basically a form up to multiplication by a constant form of degree d, homogeneous form of degree d, and a linear form up to multiplication by constant. And we have a natural group acting here, SL n plus 2, and we're going to consider doing GIT on this. Now, when I do GIT, I'm going to have to choose a polarizations of H. So for this, I need to know what the Picard group, the G linearized line bundles are, or the G invariant line bundles are. All of them are the same. It's just what you expect. It's set cross set. Okay, so we will write just O of AB to think of an element here, and this is ample if and only if both A and B are positive. And you know, the identification is the expected one, just by projecting and then taking the pullback and tensoring with the pullback of the other projection. So yeah, okay. So I define I define the quotient of the semi-stable locus by the group. So I write T, where T is B over A, because you know this is isomorphic to the projectivization of the invariant ring. Given by this. And you know, if I just change, sorry, this is MA and B. And if I just multiply AB by an integer, by a positive integer, you know, this doesn't change, so I can really just rescale by. I can just you know, just consider the quotient of these two, and I just think of T parameterizing the different compactifications. So actually, in principle, I have a one-dimensional space of stability conditions, but in practice, this is not the case, because most of the compactifications are actually the same, or saying it differently, as T moves in an interval, the empty bar remains invariant. So I have a theorem / summary of the behavior we encounter. I envy those who gave the talk on the third floor. Okay, so what's the theorem / summary? So this is so first, we don't really have semi-stable points unless T is in this interval. Okay. 2, if X is Fano, so that's equivalent of saying that D is smaller or equal than n plus 1, and XH is semi-stable, then we're going to have that H is not contained in the support of X. So what does this mean? It means that to each pair X8, I really can, so I can associate to X8 the log pair X comma D, X intersection H, and think of empty bar as moduli of log pairs. Okay. Was the third fact, what I was saying. So I don't have like the, I mean, you probably know this, but the moduli doesn't, these GATs don't change continuously as T varies. This is actually, this segment where we have semi-stable points is actually tessellated breaks into a wall chamber structure where empty bar is constant in chambers. Constant in chambers. And I mean, I could say more. This is actually known thanks to work of Dolgachev and Hu or Thaddeus. So what we actually do with this respect is that we actually can give, you give us N and D, I can tell you what the wall and the chambers are running an algorithm. I could say more about the structure of that, but we're not really going to go away from the first chamber today. So our focus today is n equal 2, d equal 3. So that means that d given by x intersection h is an anticanonical section, and x is cubic surface. So kx squared is 3. And the first chamber is given by 0 and 1/5. And we have that xd is what we call GIT T stable if and only if x has at worst A2 singularities, and if x is singular at P in D, so x is singular at a point, and that point is on the divisor. Okay, I have my surface as a bad singular point P, and P belongs to the divisor. Then P is an A1 singularity of x. Okay. So we have this explicit classification of stable points in the first chamber. We actually have it for all the chambers, but we're only going to use the first one. The second point is that xd is GITT polystable if and only if x is this equation that appeared the other day, I think, in Yuchen's talk, and D is x intersection W0. So what is this? This is the cubic surface with 3 A2 singularities. Okay, 1, 2, 3. And these the 3 lines that pass through the 3 A2 singularities. Is toric and is the unique cubic surface with 3 A2 singularities. Okay, right. So this will come useful later. Why? Because we are only going to move in this chamber, and we'll see later why. We're only going to have to deal with these two kind of singularities, and it will be very easy to do explicit work on them. Okay. So I'm allowed a little bit of extra time, right? Because we started. All right, so what's our main result? So for beta between this beta 0 and 1, there is a natural homeomorphism between the Gromov-Hausdorff compactification MGH bar GH for Gromov-Hausdorff of these pairs X of beta of log K polystable X 1 minus beta D, where X is del pezzo of degree 3 and D is E minus Kx, which a priori we don't know it's a cubic surface. Okay, I mean cubic surfaces are certainly there, but we don't know a priori that all the ones appear in our cubic surfaces, that we're not going to have some of them with horrible singularities that cannot be embedded in P3. And so the homeomorphism is between log K polystable pairs like this and T of beta bar, where T of beta comes given by 1 minus beta. Okay. And so if you plug beta in this interval, T is strictly contained inside this interval. Okay, so this is what, I mean, we are going to be always inside that compactification I described there. Okay. All right, so this is the main theorem. And now I have to make a choice, which is to sell the other main theorem that I won't prove because of time. So I think I'm just going to sell it now, make comments about it, and then just focus on this one. So there is this gap conjecture by Spotty and Sun that says that if P in W is a KLT singularity and the dimension of W is n, then the uniform normalized volume of valuations at the singularity, which we'll write as ball hat WP, which I believe is now standard notation, should be smaller or equal than 2 times n minus 1 to the power of n. So this holds for n equal 2 by, I believe, work of Liu. Is that? I think that's true. Okay, and by at n equal 3 in work of Liu and Su. Is that correct? Yeah. And I think higher dimensions is not known.
You may add Lia
Okay. Thanks. And higher dimensions, as far as I know, is open. Yeah. Okay, great. So prove or disprove this. I would be very happy with either situation.
When you say uniform, you mean like you get this upper bounds uniformly over all your issues?
That's right. That's right. Yeah. Okay. So the main theorem to says if the conjecture holds, then for all d bigger or equal than n plus 1, there exists beta 0 depending only on d and n, such that for all beta in that interval, the Gromov-Hausdorff compactification of log K polystable pairs Pn 1 minus beta. Let me write HD to avoid confusion. HD, where HD is degree hypersurface, is homeomorphic to the GIT quotient of hypersurfaces in Pn. Okay, and we have a non-optimal bound beta 0. Non-optimal beta 0. You can take it to be 1 minus n plus 1 over d, 1 minus the square root of n2, 1 minus 1 over n. Okay. And this horrendous expression really comes in away from here. Okay. Okay. So comments that I have to say. So first of all, these homeomorphisms between the Gromov-Hausdorff compactifications and the EITs are natural. So in the sense that, to a metric that exists over a given log pair, we assign its log pair, its actual log pair in projective space, which means that actually we have also, something is log K polystable if and only if it's GIT polystable. Okay, and in fact the same with semi-stable, GIT semi-stable, log K stable, GIT stable. What else? Both results use the same proof structure, which is what we call the moduli continuity method. So the way I structured this talk, which I don't think will work with few walls, was to give two intermediate propositions as black box, one for each of the theorems, and then say, okay, so assuming those two holds, look, now I prove both theorems at the same time, where at these technical points I use the propositions, and this is why it works in a quite neat way. So probably it can be applied to many other situations. If you can prove the intermediate technical propositions in those situations. So the structure of the structure is to introduce of the proof is introduce proof structure idea. So first introduce the Chern-Mumford line bundle to characterize K stability or log K stability, and that will give us that log K polystability implies GIT polystability. Okay, to define, so this is more or less done in general with a small caveat at some point for the actual definition of GIT one is working on, to define this map, which also is at 2 points dependent on the choice of GIT space you have on the right hand side, and 3, which is general to both situations, justify homeomorphism. Okay. There's a last point I want to make about the main theorem 2, which is a conjecture that we pose by taking some distance with what we claim here and looking how the proof goes, which, I mean, if you're interested in it, you look at the paper, we can talk more about it later. You can see that it's only at one point where our conjecture is gonna, in the proof, that our conjecture digresses from the actual theorem we prove. So the conjecture is, if we let, so it's, so we let X be K polystable, Fano, and we assume that out X is reductive, so that we can talk about GIT, and assume further that we have an integer L which is big enough and divisible enough. You'll see what I mean by that in a second. Then there exists some beta 0 depending only on L and X, such that for all beta 0, beta in this interval, the Gromov-Hausdorff compactification of pairs x 1 minus beta over L d, where d is in minus L kx, is homeomorphic to this Yeti quotient, okay, where we take a trivial representation. So yeah, so basically the only thing we are doing here is just taking x to be Pn. Okay. And like, I mean, if you look at the proof, you really see there's one point where we cannot show that x has to degenerate in the Gromov-Hausdorff limit to x itself unless x is Pn. And that's really the only point where we use it, I think, mainly. Okay, so CM line bundle. So I just say the basic thing I need to say about this, because I think Julio will talk way more about this in his talk. So if we let you take a scheme X and B and a flat morphism, relative dimension, and some D in X Weyl divisor, Weyl Q divisor, which is a Q-dimensional in fibers of dimension n plus n minus 1, and then for all B in B. And L is a pi very ample line bundle on X. We further assume the restriction of pi to D is flat and proper. Then by a theorem of Knudsen and Mumford, I have that there are line bundles lambda I and lambda I tilde on B, depending only on X and D respectively, such that I can write this lambda n plus 1 and so on for k sufficiently large.
Sorry, before you erase that, what do you mean in your notation at the bottom for the EIT quotient?
So you take the, how's it called, the trivial characters. So you have a natural, I mean, you can choose different representations of the group, but you take the natural one, which I guess is determined by the trivial character. So for instance, if this was to be SLN, there will be no choices. But if it's YL, I think you have a choice. Okay? Can I? Okay. So we have this flat morphism, and since it's flat and the Hilbert polynomials on fibers is constant, so for k large enough, the Hilbert polynomials of xb and db with respect to the line bundle L are given by A0 Kn plus A1 Kn minus 1 and so on. A0 tilde Kn minus 1 and so on. Okay. And then I can define the log Cm line bundle, or Q line bundle really, with angle beta in 0, 1 with the rational. So I didn't write, but everything is really rational. Every time I write beta, I think of a rational beta. Otherwise, things become a little bit nonsense. Okay, so this log Cm line bundle is given by this expression. To A1 minus 1 minus beta H0 tilde over A0 tensor with lambda n minus 2n plus 1 tensor with lambda n tilde 1 minus beta n plus 1. Okay, I think I wrote the right expression. Okay. So in some way, this is reminiscent of a test configuration as we've seen them before. Because if you take the base to be C, and you force this pi to have a GM action, a C star action, and you force pi to, if you force X and B to have a C star action and B to be C, and you force pi to be C star equivariant, then basically what you have is the definition of test configuration. So recall a test configuration of a pair like this, where these are fiber is taking D equals C and pi to be GM equivariant for some star on curly X. So then for K sufficiently large, the sum of weights of the GM action on here and equally on this one, yeah, are polynomial. So write them. Sorry, we're out of wood chalk. So they are polynomial, and we can write them as wk b0k n plus 1 plus b plus, yeah, it's not good, is it? Plus b1 kn and so on, w tilde b0 tilde kn plus b1 tilde kn minus 1 and so on. And then the Donaldson-Futak invariant for this text configuration is 2a1 b0 minus a0 b1 over a0 plus 1 minus beta b0 tilde a0 minus a0 tilde b0 a0. Okay? Yeah, I think you're right. Yeah, I think you're right. Thanks. And the beauty of this, okay, and then I mean, you know, like, so if this is positive for all test configuration, non-negative for all test configurations, then we say that our pair is log k semi-stable and so on. So I won't bother writing that down because we are running late, and I think it's been defined 3 times already. But the beauty of this is that and it's very easy to show. It's just basically like a computation. The weight of the CM line bundle is n plus 1 factorial the Donaldson-Futak invariant. Okay, it's basically like the log CM line bundle is defined so that this formula holds. So I can just look at the CM line bundle, compute the weight, and determine what the Donaldson-Futak invariant is, which has a good advantage. We'll see in a minute. Okay. So the proof is just computation. Okay. So this is basically what I wanted to say about the CM line bundle. So now I'll state 2 results and sketch the proof of the main theorem and maybe one of the results, depending on time. Okay, so if proposition, so if we let W 1 minus beta delta to be the Gromov-Hausdorff limit of smooth, and the smooth part is crucial for the proof. The smooth Keller-Einstein pairs xi 1 minus beta I di, where these are cubic surface and these are this is in minus kxi, okay, and I let beta to be between this square root of 3 over 2 and 1. Okay, then I have that W Okay, I'm gonna try to use the end. W is a cubic surface, and with at most 82 singularities, which, if you remember, is what we had in the GIT. And so at most really is at worst. At worst 82 singularities, and delta is hyperplane section, so that means in minus kW. Okay. So maybe I'll just sketch the proof here. So the first thing is that W must be KLT, which means that it has quotient singularities because it's a surface. So locally, analytically, is C2 quotient out by a group, finite group in U2. And then, okay, let me see how I do this. So I have that minus KXI minus 1 minus beta di square is 3 beta square, which is bigger than 3 beta 0 square, which is 9/4, which is 9/4. Okay. On the other hand, because this pair is a limit of that one and the volume is constant on families, that's the same as that volume. Okay. Now by inequality of Li and Liu, we have this is smaller or equal than 1 plus 1/2 square, the normalized volume of the pair. Okay, I won't write it, of this pair, okay, of a star at the point, this star. Yeah, but that's smaller or equal than, so this number is 9/4, and then just the normalized volume of W at the point without the being just a pair, just W itself, okay? But that's 9/4, the normalized volume, C2 at over gamma at 0, and then again by a formula which I think is also due to Liu. This is 9/4, 4 over gamma. So then gamma, 9 over the order of gamma, so gamma must have order at most 3 by this inequality. And this is, sorry, my 9s and 4s are very similar. Okay. And yeah, so gamma is at most 3, so that means that P is A1 or A2. But then by the classification of Q-Gorenstein smoothable singularities, no, sorry, by the classification of Q-Gorenstein smoothable singularities, P must be A1 or A2. But then I know that a del Pezzo surface with singularities of type A1 or A2 is really a cubic surface. So I am essentially done. Okay. The second result, which, okay, well, maybe I just stay then. Second result says that if I have X with X cubic surface with at worst A2 singularities, okay. Yeah, and D is intersection of X with a hyperplane, so it's an anticanonical section, okay, and the pair X 1 minus beta d is log k semi or poly or simply stable, okay, for beta actually in 0, 1. Then xd is git t of beta semi or poly or stable, depending on what I choose, in the sense we explained before. With respect to this polarization, which actually I must say, which is ample. Okay, so how I justify that? Because this GAT stability is defined in terms of this line bundle OAB, whereas I'm talking about that. So the first thing I need to do is to so the first thing I would need to do is, let me just give you an idea. First, show that this is O of AB for T of beta equals B over A. Okay, and then I prove the contrapositive. So if this is not, say, GIT stable, then there is a one parameter subgroup that stabilizes it. Okay? Remember this equation, this is important. So I have a one parameter subgroup that stabilizes it. So say if xd is GIT beta unstable, then there is lambda destabilizing it. But then I take the orbit of, so this is a point really in the, it's represented by a point in the Hilbert scheme. I take its orbit, I take the closure of that orbit, and that represents, that basically induces it induces a test configuration. And then because I have that the weight of the test the weight which corresponds to the Hillerman criterion is negative, that means that the Donaldson-Futaki invariant is negative. So I need to have stability in the Keller-Einstein sense. It's a little bit more complicated than that, and I'm putting something under the carpet because it may happen that when I take the limit, because really this is xh, in the limit h is contained inside of x, and I have to be a bit careful with that, but we can bypass it. Yeah.
But in this case, we also get that the same bundle is sample of the full Hilbert scheme. I mean, sample around varieties which are not stable at all.
Even around things that are not pairs. For instance, when h is contained in x. But then in that case, this is really not defined in that sense. So you see, this is only defined where I can, yeah. But yes, what you're saying is true, yeah. I think that's the case. Yeah. Okay. All right. So I won't go more on that. So okay. So I want to define the sketch the proof of the main theorem. I think I have -1 minute. Proof idea for the main theorem. Is this readable? This red? Yeah, okay. Because those square chocks are just not. Right, so the first thing is we need to define a map from here to there. Okay, so we can do this basically because of the combination of these two. Okay, So if we are in the if we are in the log smooth locus, we have that everything that is Keller-Einstein and log smooth is GIT stable. So this map is defined, and everything else here is a limit. Is a Gromov-Hausdorff limit of smooth things. Yeah, and then here we prove that this cubic surface with that worst A2 singularities, and the delta is a hyperplane section. But then we showed that if it's log K polystable, then it has to be GIT polystable, so it can be associated there. Okay, so then that map is defined by the theorem plus the proposition. All right. And this is really the part that the moduli continuity method is handcrafted in a way for the problem, and everything else is pretty much the same for all the problems. So phi is injective because Keller-Einstein metrics are unique. So I cannot have two of them giving me being mapped to the same log pair here. Okay, 2. What else? So this is 1, 2. Continuity follows from Chain-Donaldson-Soon and Luna-Slice theorem. 3. The image is open and dense. Why is it open and dense? Because smooth log pairs are dense in the GIT, okay, and all of them are Keller-Einstein because log smooth or just smooth pairs are both stable and Keller-Einstein. Stable and Keller-Einstein and dense in GIT. 4. The image of phi is compact. So that means that phi is surjective. And then 5. Phi is continuous bijection between between compact space in the Gromov-Hausdorff topology here and Hausdorff space in the Euclidean topology in the GIT. So phi is a homeomorphism, basic topology theorem. And that's it, pretty much.
Any questions, comments?
Do you have any motivation why which actually you wrote that?
Yeah, so beyond having proved the case when X is Pn, we also proved another case in the papers. We took this unique cubic surface with 3 A2 singularities, and let me see if I remember. So I think we took that cubic surface with 3 A2 singularities, and then we consider all anti-canonical sections, and we prove it, basically, the conjecture in that specific case. When I do the proof of the theorem when X is Pn in the conjecture, okay, I'm talking out of memory, but I think there's really one or at most 2 points where we use the fact that X is Pn. And one of them is that the Gromov-Hausdorff, we use the Gromov-Hausdorff limit of this X when X is Pn has to be Pn itself, which is not the case in general. But in a way, that's just a shortcut because we're using this moduli continuity method to prove it. But there may be other more direct ways. Yeah. So, for instance, that's not the case for the cubic surface with 3 A2 singularities. you can find deformations of it where it goes to somewhere else. And I don't know if that answers your question. So I believe it is true, yeah, but I don't have a method or a strategy to prove it rather than one we use, which doesn't work in general.
Any other?
Could you say again why you assume that theta is rational?
Yeah, safety mainly. I don't know, for instance, in the JT spaces that we construct for log pairs, if it really makes sense of talking about real polarizations.
So you can do GIT with respect to Taylor clusters, and everything works basically the same way.
That's fine when you say it in a talk, but I'm not sure if me writing it in a paper is that. Yeah, I don't feel that comfortable. Probably yes. Yeah.
You have time between theta and after the last lecture.
Yeah. Yeah. I mean, possibly it's true. Yeah, but I don't see also any advantage by. Yeah, in a way. Also, there's the advantage that if you don't consider the real coefficients, you get for free that the walls are going to be rational. Yeah, because in the GIT, when you only consider rational coefficients, you get rational walls. So you would expect that the expected walls in the variational problem for K moduli are going to be rational if they're rational in the GIT.
If you consider the moduli space of stable vector bundles over a polarized variety or something, and you try to vary the polarization in that situation, I think we can get irrational walls in the Compton code. So there are analogous situations where it's actually beneficial.
So when you say rational walls, it means the generators of the wall are irrational?
I mean that so you're just changing the line bundle or the Cayley class in the Picard group, and I'm saying that certain things cannot be Q line bundles; they might be core line